Hello again. We are now going to get into one primary application for standard deviation and how we can use that to help determine if a data set properly represents a population of data. So does this sample properly represent a population? So and how that works is from the work of this mathematician, Chebyshev. So Chebyshev was a mathematician back a long time ago. They don't have the details, unfortunately. You can Google that. But he developed a theorem that helped us determine if this data set, if a sample data set represents a population or not. And what it says is for any set of data, any set of numbers, regardless of how they are distributed. So they could look like anything, they could have repetition, they could have any kind of shape that we want, bell-shaped curve, which you probably heard of before, but any type of distribution. The fraction of them that lies within k standard deviations of their mean, where k is greater than 1, is at least 1 minus 1 over k squared. So, all right, well, what is that really telling me? So, in general, this fraction helps determine a guaranteed minimum percentage of values that lie within a certain number of standard deviations away from the mean. So let's try to break that down even more. Let's see what happens when we use k equal to 2. If we plug in k equal to 2 into our expression here, what do we get? 1 minus 1 over 2 squared would be the starting point. And now let's break that down using the order of operations. So let's take care of that exponent first, which gives us a 4. And so now 1 minus 1/4, you can do that without showing much work, but if you wanted to show some steps, you can rewrite the 1 as 4 over 4, so it has the same denominator, minus the 1/4 equals 3/4, or 75%. So remember, we can always write a fraction as a percentage. So in this case, Chebyshev's theorem is saying that at least 75% of the data should fall within 2 standard deviations of the mean. At least. It might be more than that, but the minimum should be 75%. So let's take a look back at example 1 and see and verify if Chebyshev's theorem actually worked. Does at least 75% of the data fall within 2 standard deviations? So if we go back a couple pages here and look at example 1. So example 1, we had our mean of 278 and our standard deviation of 60.7. So let's see what those cutoffs would be. 2 standard deviations away. So we'd have to take 278 minus 2 times the standard deviation. So if we do that on our calculator, we get 156.6. And if we do the same thing, but add we get 399.4. So now if you're worried you're going to have to do this, don't. We're not doing this for this class. But it's just to show you how and why Chebyshev's theorem works. So, so now we have these two cutoffs, 156.6 and 399.4. So what Chebyshev's theorem says is that at least 75% of our original data should fall between those two cutoffs. So is that the case? Does at least 75% fall between? Well, 198 is the smallest number, so that's bigger than the minimum. And on the other side, 376, well, that's smaller than 399. So not only does 75% fall between, but 100% falls between. So that's actually a good thing. So we know that Chebyshev's theorem works for this first problem. Now again, we're not going to be doing this type of analysis, but it's just to show you how that application works. So now let's go back to what we are going to be doing. So we'll go forward a couple pages. And so we're back. So all these problems are going to be looking at is how can we get that fraction? What fraction do we get using Chebyshev's theorem? So let's try a few examples. Example 5 says, using Chebyshev's theorem, find the least possible fraction of the values in a data set lying within the given number of standard deviations of the mean. Give answers as fractions reduced to lowest terms. Now, all they're doing is giving you a number, but what are we doing with that? Well, don't overthink it. This is k. That's all they're giving you is the value of k. So now you know that you have to plug it in to that expression. So 1 minus 1 over 3 squared, and simplify that down. So as long as you use the order of operations, you'll be fine. So 1 minus 1/9, which is 9/9 minus 1/9, which equals 8/9. Done. Nice and quick. When k is a whole number, it's nice and quick. When k is not, when k is a fraction in this case, now we might have to do a little bit more work. So let's see how that works. If you think using decimals might be a way around working with fractions, don't. The decimal version makes it a lot more yucky. So instead, let's use the fraction. But we have to make sure we write it correctly. So if 5/3 is the value of k, that has to go in the denominator, and we still have to square it. Now, when you square a fraction, remember the process. All you need to do is just square the top and the bottom. So this should be equal to 1 minus 1 over 25 over 9. So now we have this mess to take care of, but there's a trick with that. Anytime you have a fraction on the bottom and a 1 on the top, you can do the following. You can rewrite it as the reciprocal. So reciprocal just means you're flipping it. So that is always the case, and you don't have to really show anything else. But now we're at the same spot we were over here, so we got to get rid of that 1. So let's change that to 25s. And again, the only reason why I'm using 25 is because that's what was the denominator over here. You don't want to use anything else except what you're dealing with. So if we subtract 9/25, so 25 minus 9 is 16. So 16 over 25. And we're done. So again, be careful of the directions though. They're going to fluctuate between saying fraction and percentage. So let's do a couple with percentage. And again, this should be on the next page. So if k is equal to 5, again, what do we get for that fraction? So if we plug in our 5 for k, follow that order of operations, and we get 24 out of 25. And that's another way to think of it. So basically, Chebyshev is saying that if there was 25 numbers in your data set, 24 of them better be within 5 standard deviations of the mean, minimum. So more likely, all of them will be there. But the minimum should be 24 out of 25 of those numbers should be within 5 standard deviations. 5 standard deviations above and 5 standard deviations below. So that's another way to think of it. Let's try 7/4. So now, I've already made a mistake, and you've probably caught it, right? The key word was percentage. I'm not done yet. I should have kept going with this problem. So let's do it real quick on the calculator. 24 divided by 25 is 0.96. Move that decimal point 2 spots. So this is actually 96%. So at least 96% of the data should be within 5 standard deviations of the mean. All right, now let's tackle part B. So 1 minus 1 over 7/4 squared. So square the bottom, 49 over 16. And then remember we can find the reciprocal. So 16 over 49. So 49 is our denominator, so we'll use that to replace our 1. And 49 minus 16, I believe it's 33. So 33 out of 49, so we want to write that as a percentage. So 33 divided by 49 is, and that's okay, but just remember to move that decimal point 2 spots. So we get 67 point, and it says to the nearest tenth. So let's round that to 1 decimal point. So that looks like it better be a 3. So 67.3% when it's 7/4 of a standard deviation. Not pretty, but doable, right? Okay, so we got one more example to do on the next page, and that'll wrap up child point 3. So see you in the next video.